All right, chapter 4, section 2, solving quadratics by graphing. All right, so first breaking down the title of this section, solving quadratics. What does it mean to solve a quadratic? Well, the term solving is one that you've been coming across several times over your entire algebra career. Solving regards actually getting x equals some solution, whatever that solution may be. So pretty much your answers throughout the remainder of this unit are going to involve some sort of x equals blob, whatever that blob is, all right? Now, the quadratics aspect of this is something that's a continuation of what we did in chapter 3. Quadratics deal with, I can describe it in two different ways. Quadratics are going to deal with these shapes, okay? This is what we dealt with in chapter 3, these parabolic quadratic U shapes that we get on a coordinate grid, right? And in chapter 3, we learned how to do sad face parabolas like those two versus a happy face parabola. Now, in chapter 3, this was based around how to graph a quadratic. In this case, it's not going to be graphing the quadratic so much. This section is about as close as it will get to actually graphing one. But it's going to be interpreting that visualization of what is a solution from that. And so when we're solving a quadratic, I can think of it in terms of the visual U shape of what a quadratic actually looks like. And what we'll find out is that we're looking for where it crosses the x-axis, x-intercepts, okay, however many there may be. And so when I'm solving a quadratic graphically, I'm looking at a visualization, a graph of a parabola of that quadratic, and I'm going to be interpreting the results that I see. Now, we're going to learn several methods throughout this chapter about how to solve a quadratic and get x equals results, okay? But this will by far be the fastest and I guess probably least efficient way to do it. But this will be the fastest way to go about finding solutions, because when it comes to just plugging in a graph, and again, you'll be allowed to have Desmos for those problems. When it comes to like creating that graph, it'll be super quick, almost instantaneous. And then you're just visually looking for those intercepts. And so whatever x value those intercepts are at, those are your solutions. And that's kind of over and done with. So most of this section's notes will be based around like, all right, what are the different ways that I could put it into Desmos? What do the solutions actually mean? Those sorts of things. And what we'll learn future ways, other ways on how to solve for x within a quadratic. So visually, we're going to have these U shapes. The other way that a quadratic can be represented, the one that we're going to be exploring most often throughout the remainder of this chapter, involves a quadratic equation, right? Where it's an actual polynomial sentence. And so the real signature of what a quadratic is within a polynomial sentence is it's going to have this x squared element. So I'm going to have a polynomial sentence. This one happens to be in standard form. That may be something that you recognize from chapter 3. But what we'll also be seeing throughout this chapter are x squared polynomials that we're asked to solve. Now, most often, we're going to be looking at it in equation form. Even the problems that you're going to have in this section, you're going to start with an equation. It'll just be that in this section, you'll plug it into Desmos. It'll pop out a visual. You'll interpret the visual for a solution. In the future, what you're going to be looking for is solving that equation, rearranging that equation, so to speak, to get x by itself. That's ultimately what it means to solve for something. All right, so right here we have a little bit of a bullet point checklist for those that like little process checklists and stuff. We'll be using this technique throughout the remainder of this unit. It's a little less important for this section, again, because of what I can plug directly into Desmos. I'll demonstrate multiple ways for you. But essentially, you're going to be given some x squared quadratic equation in some way, shape, or form. You'll see a couple of examples in a minute. The first thing you typically want to do is rearrange it into standard form. This is a term that we learned in chapter 2. Standard form refers to how the polynomial is arranged, where my highest exponents come first and it goes downward from there, it descends from there. It's also tends to be solved for y, or whatever, either y or a 0 over here. You want all the terms on one side of the equation. And what we're going to deal with mostly in this chapter is that instead of y equals, it'll be a 0 equals that polynomial sentence, that quadratic sentence. Next, you're going to want to graph it. Now, all of chapter 3 was about how to do this, where we dealt with XY tables, different ways that we could use the writing of the formula to help us figure out what it would be shaped like and look like. But even simpler in this section, we're simply going to be plugging that into Desmos.com. And again, you have that resource available to you on Big Ideas. And lastly, once you have graphed that quadratic, whatever it's given to you as, the third thing we're going to be doing is identifying x-intercepts. These x-intercepts are something that we talked about in chapter 3. We had intercept form where we were looking for where it crossed the x-axis. That's the very definition of an x-intercept. Now, this x-intercept will take on many different names. So if you need to throw these in the margin, they'll also be called roots. They'll be called solutions. They're going to be called zeros. The x-intercept is a very vital part of any graph, okay? Because it essentially is where y ends up equaling 0. Y equals 0 because it goes up or down 0, thus being locked onto the x-axis or an x-intercept. Okay, so there are really 3 kind of families of groups of types of solutions, 3 possible ways that you can kind of see this visually of what it would look like. And throughout the rest of the chapter, there are kind of 3 different families of answers that you can receive. And they're represented right here. It is possible to get 2 solutions. Again, what does solution mean here? Solution means for us an x-intercept. Okay, so whatever your parabola may look like, whatever your quadratic may look like, wherever it's positioned on the coordinate universe, okay, it's possible for this U shape to cross the x-axis twice. We can see that visually done here with this sad face parabola. Okay, but it could be anywhere on the coordinate grid, but the most amount of times that a U shape can cross the x-axis will be twice. There's no magic bend here on one side that will somehow loop back and give me a third intersection point. The most number of intersections I can get with a U shape is 2. Meaning that when I solve a quadratic, whether it's the equation form or this visual graph, it is possible for me to get x equals multiple values. Now, not an infinite number of multiple values, but definitely I can get 2 possible values for x. Now, if I was reading this graph, what would those x values be? It would literally be what x value each of these intercepts would be located at. And for that, it may be a nice convenient whole number coordinate point like this one looks to be, or it could be something fractional like this one looks to be. Okay, and we'll learn how to interpret that in just a minute. But it is also possible for a U shape to only cross the x-axis once, like this. This is a far more rare and special case scenario. The only way that this U shape, this parabola, can intersect an x-axis only once is if the extreme point, the vertex, as we learned about in chapter 3, if the vertex of the parabola of that quadratic is the only thing that's touching the x-axis. It's the only way that I can only have one intersection. Any lower that I shift this parabola or any higher, it changes the number of intersections. So the only way it can happen is if it happens to be the vertex, but it is possible. Now, it is also possible for the parabola, the U shape, to completely miss the x-axis. As you can see here, this sad face parabola is completely below the x-axis. No point on that U shape ever touches the x-axis. So in that case, it is actually possible to have no solution. No solution. So these are the 3 kind of possibilities. And your first couple of problems in your assignment for this section, it's simply going to ask you for like numbers of solutions. So it'll show you a graph and be like, well, how many times does it cross the x-axis? How many x-intercepts are there? How many zeros are there? How many roots? How many solutions? Those are all based around the same thing. How often does it cross the x-axis? In this case, twice. In this case, only once. And here, it doesn't cross at all. Okay, that doesn't mean that the parabola doesn't exist or anything. It just means that there is not a 0, not a solution for an x value there. All right, so at this point, I'm going to start showing you what you're going to see for your examples. So what will you actually see in your problem set for this section? This is the type of thing that you're going to be seeing. you're going to be given series of quadratic equations. I know these are all quadratics because my highest exponent in each of these is x squared. That x squared implies multiple things. First off, visually, that means I know it's going to end up looking something like one of those U shapes, wherever it might be on a coordinate grid. That's what it will visually look like. It'll have that curve. But also, that means that it will have one of these solution sets. It's possible, and we're going to see each of these represented in these problems. I'll tell you right now that part A is going to have 2 solutions. So it'll look something like that, or at least have 2 intersection points like that one. This one will only have 1, like that one, and this one will have none. Now, just looking at these equations, you guys don't know yet how to interpret looking at the equation to just figure out how many solutions there are. We're going to explore that with how to use Desmos to our advantage, right? Me, as a professional who's done this for years and years and years, I can figure out little tricks and hints for what I'm looking for to figure out how many solutions there are. But the fastest way, even for me as a professional, will be to use Desmos. So I'm going to go ahead and first show you the solution sheet to these notes, which is also uploaded onto Google Classroom. So this is what's uploaded onto Google Classroom. And you'll notice that I give you multiple ways in which to graphically show what's happening with each of these examples. Now, what I want to emphasize here is this. You do not need to show all 3 of these methods. Any one of them will be acceptable. And you'll notice that any one of the pieces of work I show, any one of these methods that I show, there's not a ton of work to be shown. Kind of inherent with this section, the ability to just look at a graph and interpret, pull out the information you need from that visualization. There's not a lot of computation and work that goes into that. But what's going to be the trick in this section is interpreting what you see and learning how to interpret what you see. Okay, so in each of these methods, and you'll see that the reason I wrote or in each of these is that you don't have to do all 3 of them. But in each of these cases, these are just different representations of how I could put stuff into Desmos.com. Again, most of you will be familiar with how I can write an equation into Desmos and it will automatically, instantaneously graph it for me, which is a powerful, powerful tool. So the most easy method, in my opinion, is to literally just, in our first example, we're given x squared plus 2x equals 3. I can literally just type that as it is into Desmos.com, and it's going to spit out this graph. Now, interpreting what visually that means will be the trick, because I could put anything I want into Desmos, but if I don't know what I'm looking at, it didn't really help me a whole lot. Okay, so if you just put in the equation as it is, in this case, x squared plus 2x equals 3, it spits out these 2 vertical lines right here on the coordinate grid. And I'll show you what that looks like in a minute. But I wanted to kind of talk about what we're seeing first. These 2 vertical lines that pop out, this is literally solving the equation for you. What it's telling you is like it's doing all whatever algebra work, whatever magical things happening here, it's doing it automatically for you. And the way you would interpret your answers, where those vertical lines are positioned. So for instance, this one right here, this one on the right, it's located 1 to the right. That means that x equals positive 1. That's where the x-intercept is right there. X equals positive 1. What does that actually mean? If I were to take that positive 1 and plug it back in to my original quadratic equation, it should make sense. It should check out. Okay, not every value I plug in for x here will work. Only a couple will. Now, that x equals 1, if I were to plug it in, and I'd say do 1 squared plus 2 times 1 equals 3, I'd end up getting 1 plus 2 equals 3. That makes sense. It's a logical statement. That means that positive 1 is a solution to that equation. Now, this other vertical line, located 3 to the left, meaning that x equals negative 3, that's the other solution here. So if I were to take that negative 3 and plug it back into this quadratic equation, I would get negative 3 squared plus 2 times a negative 3. That would give me 9 minus 6 gives me 3. That is also true. Literally what this means is that both of these values, negative 3 and positive 1, will satisfy that equation. Those are the two solutions. Now, that's just the fast way to do it. Nothing really went into it work-wise other than typing exactly what you saw for the quadratic equation into Desmos.com, and then just looking at where the vertical lines cross the x-axis. Those are your answers. X equals +1, x equals -3. Another way to do it would be to take each side of that equation and graph each of them. So for instance here, the left side says x squared plus 2x. If I were to graph that, x squared plus 2x, it would give me this green parabola right here. And that makes sense because it's x squared. Now, if I were to graph the right-hand side of the equation, the +3, that's this blue equation right here, that would end up being a horizontal line, y equals 3. And what I'm looking for in this case, this is a concept that's pulled from Math 1. This is called a system of equations. I'm looking for intersection points between the two graphs. And as you can see, they intersect in two spots. This horizontal line that we graphed with y equals +3, this horizontal line crossed in two different places on that parabola. Those x values turn out to be the same exact x values as our other one, which makes sense. I shouldn't get magically different solutions here. All right, so that's just another way to plug them into Desmos. And then finally over here, this is a little bit more like the technique that I demonstrated with those bullet points at the beginning of the notes. The idea of reworking this equation into standard form. Basically, move all the terms onto one side of the equation. So in other words, I have x squared plus 2x on the left. If I want to move this 3 across the equal sign, I would have to subtract it from each side. Now I would get x squared plus 2x minus 3. And if I were to graph that, that would give me this parabola. And now in this case, like the bullet point said at the beginning of our notes, I'm looking for x-intercepts, which there are 2. And lo and behold, they happen to be at the same exact x-intercepts as the original. So each of these is just a different way that you'll get the same answers each time. It's just that whatever you prefer, okay, whether you want to do the standard form thing, we're going to be exploring this more often as far as solving things algebraically on paper with this kind of stuff in future sections. This kind of method isn't terribly difficult, just moving all the stuff onto one side of the equation. This one's even simpler. You just write it into Desmos exactly as it's written, and it's going to spit out this crazy looking graph. All right, so let me show you on Desmos. I'll go ahead and leave this on the screen right now. Let's see on Desmos what this will look like. So I'm going to share screen right now. Many of you are familiar with Desmos. You've dealt with it in some way, shape, or form in the past. But this will be a worthy tutorial again because you'll be using it. All right, so for those that have never been to Desmos.com, when you first visit Desmos.com, it'll have like a page with all these different things on it. You're going to look for the blue button that says Start Graphing. Click on that, and that will lead you here. Okay, so here on Desmos, we see we're given a coordinate grid, and it's going to give us this little function tab on the side. This is where we're going to be plugging in our equations. So literally, for my first example, if I just type it as it is written, that would be x squared plus 2x. And you'll notice, first off, as soon as I typed in the x squared, it showed me that parabola. Literally, it is instantaneously graphing whatever it is you're typing in. And this makes sense because that is the parabolic, the quadratic type of shape that you get with x squared. But if I add another element like the plus 2x, you'll notice that it shifted a little bit, moved down and to the left a little bit. That was part of what we learned in chapter 3 as well, about how those other elements move around this graph of a quadratic. But finishing out the rest of the equation we were given, the equals 3 element, we'll see those two parallel lines I just kind of talked through on our assignment. So on your assignment, as you're doing this, when you just type in the equation as it's written, you're going to get these series of parallel vertical lines. How do you interpret what you're seeing? You're looking at the x-intercepts. There's the +1. There's the -3. Those are your two solutions. All right, well, let's see what happens if I were to rewrite that as just a regular quadratic. So in this case, if it were x squared and then plus 2x, but then I had moved that 3 to the other side and made it minus 3. There's the actual parabola if I were to graph it in standard form, and you'll still see the same two x-intercepts, positive 1 and negative 3. All right, well, our second example is a little bit different. Now we're given x squared. All right, there's our x squared parabola. But now it says minus 8x, so you'll notice that this shifts around a little bit differently. Now it's way down to the right. And then we're given equals negative 16. Now here you'll notice that there's something a little bit different with this one than the previous example. You'll notice that there's only a single vertical line. This implies that there's only one solution. Even if I were to like zoom way out, you see there's still only one, just in case there's a wild number out there. But this solution, the answer is 4. Again, the x value in that coordinate point. What does that 4 mean? If I were to take that 4 and plug it back into this quadratic equation, it should make sense. And lo and behold, if I were to plug in 4 squared gives me 16. 4 times that negative 8 is negative 32. Positive 16 minus 32 gives me negative 16. It checks out. So what happens if I were to take that negative 16 and move it to the other side, making this a standard form quadratic? So if I were to add it to the other side, oops, let me get rid of that. So now it would be plus 16. And there's the actual graphed parabola like we would have done in chapter 3. And here's where you will notice that it only crosses the x-axis once. This is the extreme point, the vertex of that parabola. That is the only thing touching the x-axis, therefore the only solution to this parabola. All right, one last example to run through. Our last one, we are given a negative x squared. And you will notice that immediately it is now a sad face parabola. That makes sense because it was a negative in front of that x squared. And then we're told it equals 2x plus 4. Oh, well, this looks pretty blank. Even if I zoom out, I don't see anything. I zoom back in, there's nothing there. What does this mean? This literally means that there is no solution. There are no solutions that it's given me on this x-axis. So this is the case where had I graphed this standard form parabola, it should completely miss the x-axis. And so let's see what happens if I were to do that. Say if I were to move that 2x and that positive 4 over to the other side by subtracting them. Let's see what would happen, right? So I'd have minus 2x and then minus 4. And there's the actual standard form of that parabola where you see it is a real parabola. It's not like it doesn't exist. But what we also notice is that it does not cross the x-axis. It does not touch it at all. It's completely below it. And because it's completely below it, there is no real solution to the x here. Again, what that literally means back in this equation form, negative x squared equals 2x plus 4. What that literally means in an equation form is that there is no value for x that I could possibly plug in here. No weird decimal, no weird fraction. There is nothing that exists for x that I could plug into this equation that will ever make it make sense. It will always end up with some number equaling some other number. That's not possible. I might end up with something that says like, all right, well, it might be negative 16 equals 12. Well, that's not true. Negative 16 is negative 16 and 12 is 12. What that means is there is no x value that I can plug into this equation that will ever make it make sense. That means that there is no real solution. That's what that means. And that's how you can use Desmos to your advantage. All right, so at this point, I'm going to go ahead and stop recording.